All right, welcome to the second vodcast for your study guide. We're going to pick up at number 11 now, and but before we get started, I just want to kind of show you guys some of the typos that I've been finding so far. So if you can drop down to number 17 on your study guide, pretty much everything in number 17 that said K, potassium, can you change that to say Ag, silver? All right, so anything that had a K on there, I want you to switch it to be silver, Ag. Ag. All right, now that we've taken care of that, let's go ahead and start on number 11. Let's do it. Okay, so number 11 has you guys starting off with, let me just double check. Number 11 has you guys starting off with 134.5 milliliters of water. And it didn't really specify whether or not this is gaseous water or liquid water. So if it doesn't say, I want you guys to go ahead and assume that it is a gas at STP. All right, that's going to make your life a lot easier. Otherwise, we'd have to do a quick density conversion. Ooh, that's fun. What's the density of water? 1. So you could technically change the milliliters to grams, and then you could just start the whole problem that way. But we're just going to assume that this is gaseous water. So on number 11, they're starting you with 134.5 milliliters. All right, I'm praying that you got your metric conversions down after the last video, okay? So 1,000 milliliters is equivalent to 1 liter. So what am I doing here? I'm basically converting to liters. Why? Come down here, have a plan, okay? This time what you're doing is you're starting with volume down here at the bottom. And in number 11, they want you to solve for moles, molecules, atoms of hydrogen, and atoms of oxygen. And so you're going to need to do a conversion for all of that. All right, so basically what we're going to do is we're going to make a quick little pit stop on the mole, and then we'll come over here and we'll talk about the representative particle. So remember, we're dealing with water, and water is a molecule. So when you use Avogadro's number, you're not getting to atoms yet, okay, because water is a molecule. So we'll hit molecule first, and then if we have to go to atoms, we'll do that last little tiny piece where you have to get to the representative particle. All right, so very first thing I've got here is I've got the liters. They want moles. So what conversion are you thinking in your head if you're on liters and you need to go to moles? Very good, 22.4. And that's how many liters are equivalent to 1 mole of gas at STP. So cross-cancel units. 22.4 liters goes down, 1 mole goes up, because you have to cross-cancel your liters. So stop here, grab a calculator, let's check our work. 134.5 divided by 1,000 and divided by 22.4. Okay, calculator says 0.00600044, and it keeps going like that. How many sig figs do you want here on this answer? 3. Do zeros in the front count? No. 1, 2, 3. Do you need to round the 0 up? No. So technically your answer is 0.00600 moles. That's just one of the answers that they're looking for. Okay. Don't hit clear on your calculator. Don't hit clear. Keep that answer, okay? That whole thing. Keep all of the numbers, okay? Because the next question that they will have is how many molecules is that? All right, so if I were to continue this problem, you see how we stopped, but if I were to continue the problem, and if you need to go to molecules, what should I be doing? What's your plan? Good, 6.02 times 10 to the 23rd, that's Avogadro's number. That's equivalent to 1 mole. So water, the only thing you need to ask yourself is 6.02 times 10 to the 23rd, what's? Molecules, okay, good, molecules. All right, so cross-canceling moles. How many moles? Look, 1. So basically, you left that answer on your calculator, right? Multiply. Hey, do you want to go to another room or anything? Am I too loud? You sure? It's all good? Sweet. I'll take it from you. It's pretty fast. Good for you. Cool. So since you stored your answer, all you have to do is hit times 6.02 times 10 to the 23rd. Now, notice I'm not rounding, okay, because I used that stored answer. This is what I get on the calculator when I multiply by Avogadro. Hold on. Times 10 to the 21st. So you need to reduce this still to 3 sig figs, 1, 2, 3. Do you need around that 1? No. Do you guys confirm? All right, I'm always kind of checking that, make sure I don't have any mistakes. All right, so this is how many molecules there are. Okay. And I still have my stored answer sitting on my calculator. All right, so if we were to continue this problem and try to solve for atoms, atoms of hydrogen, atoms of oxygen. So let's just kind of pretend like I want to go to atoms of hydrogen. So if this is how many molecules of H2O, think about H2O. Look at that formula. Each one molecule of H2O has how many oxygens, how many hydrogens? 2 oxygen atoms and technically 1 hydrogen atom. Oh my God, I can't believe I just did that on a video. Leave me alone, I'm sorry, that's wrong. 1 oxygen, 2 hydrogen. Fantastic. At least someone's awake around here. Thank you guys. All right, shall we then? All right, so 1 molecule of water is going to contain 2 hydrogen atoms. Okay, so I have a stored answer, this one right here. I have that answer kind of stored on my calculator. I didn't hit clear. So all I'm going to do is I'm going to take that stored answer and I'm going to hit times 2. And on my calculator I get 7.22937, and it keeps going, times 10 to the 21st. And that's going to represent how many hydrogen atoms you have. But what about sig figs? Maintain those suckers. 1, 2, 3. Do I need to round that 2? Yeah, so this is actually going to be 7.23 times 10 to the 21st, and that would be hydrogen atoms. Okay, so that's how many hydrogen atoms you have. So if I had to go from molecules to now oxygen atoms, what would this ratio look like? It would be 1 to 1, huh? So however many molecules you have is how many oxygen atoms you have. So it's going to be the same answer. So over here, there are 3.61 times 10 to the 21st, and now you're going to say oxygen atoms. And there you go. That's everything that they asked you for. Okay, any clarification questions on that one? It's all good? Okay, that was number 11. Let's keep going. Number 12. What are the 5 types of chemical reactions? And give an example of each. So I'm going to cheat because I already did a key on this one. So let's just talk a little bit about what I said on my key. Right here. Oops. Okay. All right, so there are 5 types of chemical reactions: synthesis, decomposition, single replacement, double replacement, and combustion, correct? All right. So I gave real examples for each. You don't have to if you don't want to, but I think it's good to expose you guys to this content. So in a synthesis reaction, you can have 2 elements that combine to make a compound. So I chose hydrogen and oxygen because that's like rocket fuel, and we've talked a lot about those micro rockets. Let's see, in decomposition, we just recently learned in the last lab, in your acid lab, that anytime you see carbonic acid as a product, it decomposes. Do you guys remember that? Okay, so carbonic acid is not a very strong acid. It's a weak acid, and it naturally decomposes into H2O and CO2. So you start with like a big compound, it breaks down into smaller parts. A single replacement reaction relies on your metal reactivity series. So I'm giving you guys a really good example. You've got silver nitrate, and that's a solution, and we're going to dump in some pure sodium metal. On the metal reactivity series, sodium, I hope, because I did this earlier, is sodium more or less reactive than silver? It's more reactive. Yeah, silver's down at the bottom. So then you're going to have a single replacement work. So the lone element has to be higher in reactivity, and it is. So then they're going to switch places, and silver has a +1 charge, and sodium has a -1 charge, or +1 charge, so they both are +1, so it was like a perfect swap out. All right, in a double replacement reaction, you're going to look for two different situations. Either you have a precipitate, or you made water. Okay, those are the two situations that will make a reaction work. So I chose some sodium chloride, that's a solution, some sodium nitrate, that's also a solution. And when they switch places, the sodium and the silver, you'll make some sodium nitrate, which is soluble, but then this dude right here, the silver chloride, this is insoluble, and so that'll be your precipitate. And finally, the last one is combustion. In a combustion reaction, you're going to have some kind of hydrocarbon. I chose a very simple hydrocarbon. And that hydrocarbon is going to react with oxygen, and you will always make CO2 and H2O. So then my question would be to the class. Is this a combustion reaction? Why could it sometimes be like confused as a combustion reaction? Yeah, you're adding oxygen, and look, you're making water, huh? So, and I mean, on top of that, you guys know that that makes a pretty loud pop, a pretty good little snap, right? The reaction is vigorous. So, I mean, I totally understand. It kind of could be considered combustion, but for our purposes here in honors chemistry, this is going to be a synthesis reaction for you guys, just to keep it consistent. All right, peeps? All right, 5 types of reactions, done. All right, so that was number 12. Let's look at number 13. Balance the following, and then identify what type of reaction they are. All right, all right. So, recommend what you'll do on this one is to put a little line in the front of each of your substances so that you can easily balance these. Okay, notice they don't give you the products. Again, this is number 13. They don't give you the products. Can you tell what kind of reaction it is just by looking at the reactants? Yeah, you can. This is a combustion reaction, huh? What are the two products in a combustion? CO2 and H2O, you got it. All right, so starting off, what we like to do sometimes is an atom inventory. So we'll count how many carbon, hydrogen, and oxygen we have on the left, and then we'll do it again for the stuff on the right on the products. Carbon over here is 2, this is 6, this is 2, that's 1, 2, and 3. Okay, so some guidelines. Balance the atom that you see the most of across the board on the reaction. Balance that one last. Let me show what I mean. Up here I see carbon here, and I see carbon here. I see carbon twice. Hydrogen I see here, and here. I see it twice. But look at your oxygen. Here, here, and here. Oxygen is going to be the most difficult element to balance, so balance him last. So let's go ahead and try to start with the carbon. On the left you have 2, on the right you have 1. Your carbon is right here, so let's just try this and see what happens. That'll give us 2. Oxygen, careful, you have 4 here, and another one right there, so that gives you 5. All right, balance oxygen last, right? So let's move on to hydrogen next. Hydrogen is 6 on the left, 2 on the right, so let's try to get 6 hydrogen. Here's your hydrogen. I want 6, so I'm going to try to place a 3 here. That'll do that. Now watch this. 4 oxygens plus 3. What's 4 plus 3? 7. Okay, so the reason why I chose this as an example is because you've seen this situation before, where everything balances except for one element. And in particular, what you have is something called an odd-even combination. Over on the left, you see this O2. No matter what coefficient I place on this, it's always going to be an even value for your oxygen atoms. Now on the right, you have water. Do you see this 3 right here? If you place an odd value in front of this water, you will have an odd number of oxygen atoms. So am I allowed to have an odd number here? No. So there's a really cool solution that you can do in order to fix this entire thing. Everything you balanced, you see all the coefficients, you see the 2 and the 3? Double it. And your hydrocarbon. All right, so I'm going to change this 2 to a 4. I'm going to change this 3 to a 6, and I'm going to double up on my hydrocarbon. So let's just kind of recount everything. Carbon is 4, Hydrogen is 12 now. Let's see what happened to our oxygen now on the right side on the products. All right, so on the CO2, how many oxygens do you have with the 4 in the front? That's 8. And then you have 6 over here, right? So what's 8 and 6? You have 14. Let's go over to the left side for a minute and look over here. Since I placed that 2 in front of the hydrocarbon, this guy right here is going to change to a 4. The 6 is a 12 now. All right, so obviously we're just balancing that oxygen. That's what we need to do. So if I need 14 oxygens on the left, here's oxygen. What am I going to place in the front right there? 7, you got it. So there you go, you just balanced it. 2, 7, 4, 6. And that was actually just part A. Okay? All right, let's go to part B. Okay, we got aluminum and some oxygen. And they don't tell you the products, but you're going to figure this out. So aluminum is an element, and O2 is the elemental form of oxygen. Any ideas what a metal and a non-metal are going to want to do in life? Yeah, they're going to want to date. They're going to want to go out steady. Yeah, they're going to hook up. All right, so the aluminum and oxygen are going to make an ionic compound, obviously aluminum oxide. Now, when you bring elements like that together, what do you have to always balance? Yeah, charges. So aluminum, element 13, he's closest to neon. He's going to lose 3 electrons, so he's going to have a positive 3 charge. What about oxygen? Yeah, he's going to gain 2, so he's going to have a negative 2. All right, 3-2 combo. So what's the common multiplier? 6. So we'll have 2 aluminums and 3 oxygens. That's the compound that those two will make. So anytime you have to make a compound, you better check it to see if you need to balance those charges first. All right, now that we got the compounds and everything's all written out, balance the reaction. Okay, so let's go for, oh, by the way, I almost forgot, on number 13, part A, what type of reaction is this? I said it, but I didn't write it down. Yeah, this is combustion. Combustion reaction. Can you tell me what kind of reaction B is? Yeah, this is synthesis. Okay. All right, so if you want to, we can break this down again and do kind of an atom inventory, if you will. Aluminum and oxygen, aluminum and oxygen, 2, 3, this is 1, and this is 2. All right, I'm going to kind of zero you in on the oxygen because I see it. I don't know if you guys see it, but you have a 2-3 combo. What's a common multiplier for 2 and 3? 6. So on the left, let's try to get some 6 oxygens. So what am I going to place in the front? 3. Okay, so that gives me 6. Now oxygen here, if I want to get 6, what am I going to place in the front right here? Yeah, I'm going to stick a 2 right there. Now that's going to change both of these, right? How many aluminums do you have now? Okay, and now you need 4 aluminums on the left. There you go. And that was B. Okay, everyone doing okay? So 13C. 13C, look like this. Okay, and they don't tell you the products. Can you guess, though? First of all, what kind of reaction do you think this is going to be? Double replacement, and specifically when you see the H in the front and the OH in the back of the other dude, that's a neutralization reaction. Ring a bell? Okay, you got an acid and a base. So who's the hydrogen going to hook up with on the other side? Yes. Yeah, hydrogen hydroxide is otherwise known as water. All right, and then who's magnesium's new buddy? Chlorine. So magnesium has a positive 2 and chlorine has a -1, so you want to kind of check those charges again. Remember, anytime you make products like that, compounds, you got to check your charges. All right, this one's pretty easy to balance. Do you guys see it? Water only has 1 hydrogen and 1 hydroxide. So you see how there's 2 hydroxides right there? Let's stick a 2 right there. But if I do that, you see how there's 2 chlorines, and this now has basically 2 hydrogen ions, 2 hydroxides, so I'm going to place a 2 right there. I didn't do an atom inventory on that because it's a double replacement. It's pretty easy. Well, I guess we're going to have to call it quits here. Maybe I'll continue in IC. Huh? Fun, fun.